Force, mass and acceleration. We can investigate the relationship between force, mass and acceleration using this apparatus. We have an air track on which rides a truck with a blanking card of a known length. This is attached to a piece of string through a pulley to a mass. This gives the accelerating force due to the weight of these masses. As the card passes through the light gates, the speed here and the speed here can be found and the acceleration calculated. Generally, the light gates would be connected to a data logger that would do all these calculations for us. If we keep the mass of the truck constant and change the force, plotting a graph of acceleration against force gives us a straight line through the origin. This shows us that acceleration is directly proportional to force. This means that as you double force, acceleration doubles, treble the force, acceleration trebles, and so on. We generally write this as A is directly proportional to F. We could say that force is equal to a constant times acceleration. If we keep the force constant and change the mass, plotting a graph of acceleration against 1 over the mass also gives us a straight line through the origin. This shows us that acceleration is inversely proportional to mass, which we can write as A is directly proportional to 1 over mass. We could then say that force is equal to a constant over the mass. We can combine these two equations and write that force is equal to a mass times acceleration. This is by making our constant 1 and applies as long as the force is in newtons, the mass in kilograms, and the acceleration in meters per second squared. Let's look at a problem using this equation. Find the acceleration of a skier of mass 80 kilograms on a slope at 24 degrees to the horizontal if frictional forces of 120 newtons are acting. Well, first we'll draw our slope at 24 degrees to the horizontal, add the skier with a frictional force opposing motion, that is up the slope, of 120 newtons. The skier's weight will act vertically downwards, and I've drawn a normal to the slope. This angle here will be 24 degrees. We want to find the component of the weight W acting down the slope, that is resolving away from the 24 degrees, meaning this force will be W sine 24 degrees. But W is the weight, which is the mass times gravitational field strength, 80 kilograms times 9.81 newtons per kilogram from your datasheet, giving W equal to 784.8 newtons. The force down the slope will be equal to W sine 24 minus the frictional force of 120 newtons acting up the slope. Putting the numbers in, that's 319.2 newtons for W sine 24 minus 120 newtons gives a total force of 199.2 newtons down the slope. Using A equals F over m, that then gives 199.2 newtons over 80 kilograms, giving an acceleration down the slope of 2.5 meters per second squared.